Bismillahirrahmanirrahim. Chapter 37. According to our syllabus, this is chapter 10, right? Diffraction patterns and polarizations. So, in previous topic, chapter 34, we briefly introduced the notion of diffraction, a phenomenon that occurs when wave pass through an aperture or pass an edge. Okay, in chapter 36, we begin our investigation into physical optics, in which we study the particular phenomenon that occur due to the wave nature of lights. Diffractions was important to the understanding of interference from double slits in this chapter. In this chapter, we will extend those discussions and expand our understanding of diffractions. We will also study the interesting phenomenon of polarization, which is important for light wave but impossible for sound wave. Introduction to diffraction patterns, right? We discussed that light of wavelength comparable to or larger than the width of a slit in a barrier spreads out in all directions beyond the barrier upon passing through the slit. Okay, this phenomenon is called diffraction, as we've seen in previous topics, where you have a barrier, okay, and this is, let's say, wave front that coming, okay, this is a barrier, let's say. So if the opening of the aperture or the barrier is small enough, okay, from the wavelength, the wave going to be diffracted. Okay, this is what I'm saying about just now. Okay, other wave such as sound wave and water wave also have this property of spreading when passing through aperture or sharp edge. Okay, based on this spreading of lights as it passes through an opening, we might expect that the light passing through a small opening would simply result in a broad region of light on screen, but that is not so, isn't it? We find something more interesting, however. A diffraction pattern consisting of lights and dark fringes, dark area, is observed, like that shown in figure here. Okay, this is, let's say, the output of this situation. Okay. The pattern consists of broad, intense, central bright, okay, or band. We call it central maxima, this one, right? Flanked by a series of narrower, less intense additional bands called side maxima or secondary maxima here, right? And series of intervening dark bands, or we call it minima. Okay, in this figure shows a diffraction pattern associated with light passing by edge. Okay, this is opaque object. Okay, this is the source of the lights. The light is passing the edge of this object. Again, we see bright and dark fringes, which is reminiscent of an interference pattern. Even though we don't have a barrier with a slit like this, this pattern produced as a proof that, okay, the lights being diffracted and interference happened, because by right we should see only a clear or bright area in this pattern, in this part, because this is the opaque object. So by right, the lights only travel and fulfill the viewing screen on the upper part only. However, we see here alternating bright and dark fringes. This as a proof that interference happen for the lights. Okay, now this is actually a diffraction pattern created by illumination of a penny with a laser. Okay, with the penny positioned midway between the screen and the laser. So if you want to visualize how is this happen, let's say this is a laser beam. Okay, passing through, coming from a coherent source. Okay, passing through a penny. Right, and here you have a viewing screen. Right, so what will happen? Okay, the image of this observed on the screen here is like this one. So this is the image of the opaque penny. However, at the edge of the after the edge of the penny, there is a alternating fringes. And another interesting that at the center of the image of the penny, there is a bright spot. Okay, where it proves that due to the equidistant of the center from all points on the edge. Okay, so equidistant. Right. The light from all points will interfere constructively there at this point, causing a bright spot to be seen. Okay. This is subtopic 37.2, diffraction pattern from a narrow slide. It is named as Fraunhofer diffraction pattern because Fraunhofer suggests that we put a lens here to focus, to have an even better image on the screen. Okay, so let's take a look in detail on how the experiment being done. Okay, so we have incoming wave, right, that going to pass through a narrow opening model as a slit and projected onto a screen, okay, that is far away, much bigger, the L much bigger compared to the size of the opening. Okay, this is a must. We can explain some important features of the phenomenon by examining wave coming from various portions of the slit as shown in this figure. Okay, according to the Huygens principle, each portion of the slit acts as a source of light, of wave. Okay, hence, light from one portion of the slit can interfere with light from other portion, and the resultant light intensity on a viewing screen depends on the direction of the theta here. Based on this analysis, we recognize that a diffraction pattern is actually an interference pattern in which the different sources of lights are different portions of the single slit. Okay, therefore, the diffraction pattern we discuss in this chapter are application of this wave in interference analysis model. Right, so we're going to apply the same approach. Okay, to analyze the diffraction pattern, let's divide the slit into two halves. Okay, as shown in this figure. So, from one single slit, now we divide it into half, into two. So, each of it having A/2 of length or separation or opening. Keeping in mind that all of the wave are in phase as they leave the slit. Consider now ray 1 and ray 3. Okay. As these two rays travel towards a viewing screen far to the right of the figure, ray 1 travels further compared to ray 3, okay, by this distance. So this is the path difference between ray 1 and ray 3, because ray 1 need to travel further by this path difference. So the distance here according to this triangle is actually a over 2 sine theta, where a is the width of the slit, the original slit. Similarly, the path difference between ray 2 and 4, okay, is also a over 2 sine theta, as is that between ray 3 and 5 as well. If this path difference is exactly half a wavelength corresponding to the phase difference of 180 degree, okay, which is half wavelength, right? Therefore, wave from the upper half of the slit interfere disruptively with the wave on the lower part, okay, or lower half of the slit. Okay, so okay, a over 2 sine theta is equivalent to lambda over 2. Why is it lambda over 2? This is for the disruptive interference, okay, in the order of half wavelength or 180 degree. So rearrange this equation. Sine theta is equivalent to lambda over a. Plus minus mean upper part of the screen or lower part of the screen. If we are dividing the a firstly into half, now into 4, okay, separated into 4 portions. Again, we are going to see this is the pattern of the equation for sine theta. Sine theta is equivalent to plus minus 2 times lambda over a. This is the lambda over a. So here 2 times of this, right? If we divide the separation, the slit, into 6 portions, again we are going to see the similar pattern is repeated. 3 times lambda over a. So in general, sine theta dark, because the original of the formula talking about disruptive interference, is equivalent to m lambda over a, where the m is equivalent to plus minus 1, 2, 3 and so on. There is no 0 for m, because at the center of the viewing screen we observe central maxima or constructive interference or bright fringe. Basically, for this setup, we are going to apply this equation. So bear in mind that sine theta dark is equivalent to m lambda over a, where the m is 1, 2, 3 and so on. Positive, negative representing whether it's upper part of the screen or lower part of the screen. If we notice here, for a single slit, there is no formula or equation for the bright fringes. However, the width of the central maxima is twice, okay, the position for the first dark fringe. Okay, so if we put it like this, so the width will be y1 upper part plus y1 lower part. So here is the width of the central maxima. So let's take a look on conceptual example 37.1. Where are the dark fringe? Light of wavelength 580 nanometer is incident on a slit. This is how we know this is a story of single slit. Normally it's not going to state it single. When it put a slit, understood this is single slit. Having a width of 0.3 millimeter. The viewing screen is 2 meters from the slit. Find the width of the central bright fringe. Okay, so what we have in our hand, sine theta dark is equivalent to plus minus lambda over A. Okay, what about the M? Because we want to have the width of the central maxima confirmed, the M going to be 1. Okay, positive 1 and negative 1. Upper part of the screen, lower part of the screen. So 2 times of y1 position on the screen, magnitude only, okay, is equivalent to 2 times L sine theta dark. What is the sine theta dark? Is this one. Substitute here. Then you will have 2L lambda over A. From here, substitute the rest of the information, you will get the width of the central bright fringe or maxima is equivalent to 7.33 millimeter. This is on how to get the width of the central bright fringe. What if the slit width is increased by an order of magnitude to 3 mm? So means that our A now, this is our A, going to be changed, okay, into 3 mm. So we're going to repeat the same formula, the same calculation, but now our A is substitute with 3 mm. You will get 0.73 mm, which is smaller compared to the first part just now. And now, intensity of single slit diffraction patterns. So from the viewing screen image produced on viewing screen, we can relate into the intensity of the lights, okay, being diffracted via single slit. So the intensity at the center, the central bright fringe, is the most, okay, the highest, alright. But as for another flanken fringe, the intensity is reduced. Okay, you need just to understand the concept on how the intensity is reduced.